Hello everyone. As we discussed in the last class, actually, so we are going to have a quiz of HMM's hidden Markov models in the next class. Uh, I was unfortunately busy and a meeting got scheduled exactly at the same time as our class, so I had to. I could not take the class at that time, and I'm sorry for that. But what I've done is that I've made a video lecture of the whole lecture that was supposed to be held on Thursday, like 2 days ago. So I hope that this lecture is going to cover up for the actual lecture. And what I want you to do is I want you to look at each of these statements, each of these words that I'm going to tell you, and kind of figure out the different problems that we're going to face and see. So what I've done is I'm opening this HMM paper, the one by Rabiner, and I'm quickly going to go through the basics of this, starting with Markov chains that we discussed in the previous class, and quickly building up towards the hidden Markov model and those kind of things. So starting from this paper first, let's go to this is basically chapter 8 that I sent you, and this is a very well written chapter, which is kind of introduces you to everything that was written by Rabiner, but in a rather simpler manner, right? So the idea is that we want to start off with Markov chains. Markov chains are, like we discussed earlier, you have got some observable events that are there. So for example, in this case, you can see two different Markov chains, and the possible values that a chain can have is it can be either hot on a day or a cold on a day or warm on a certain day. And if you look at the other side over here, it's basically again there are three different states. One is uniformly, one is R, and one is basically charming, right? So again there are three different states, and for each of these states you can actually move from one state to the next. So each of these states in a first order Markov chain depends only on the previous state. So for example, what is the probability that it is going to be cold tomorrow? If you have to predict that, it will only depend on the weather today. If it was cold today, then the probability of having another cold day tomorrow is going to be 0.8, because this is the arrow that controls it, right? If it was warm today, then the probability of having a cold weather tomorrow is 0.1, and if it was hot today, again the probability of having cold tomorrow is going to be 0.1. So whatever the weather we want to predict, it only depends on the current day's weather, right? Similarly, on this side, these are three different words, are uniformly charming, uniformly are charming. So they can follow, different, each word can follow another word in this case. So in this example, you have got weather followed by another day's weather. In this case, you have got different words that are followed by other words. So this is kind of the different kind of problems that we are facing in Markov chains. Is you can sense the temporal or spatial behavior of these models. So it's always that one follows the other. So whenever you have got words that are followed by other words, or for example, weather that is followed by another weather, or maybe a sequence of events, maybe if you just think about coin tosses, right? So head, 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 tail, 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 etc. Or if you think of dice numbers from 1 to 6, so if I give you a sequence of 3, 4, 5, 1, 2, 3, 1, 1, 1, etc. So all of these are what we call, these are sequences of events. And these sequence of events are dependent on the temporal direction of the graph. So it's like saying that they've got a temporal axis associated with it. And the main idea here is that what we need to do is that you need to take care of the temporal values here. So it's like one follows from another, then if it is followed by a third, and so on. And the idea of Markov chain is that it is, if we talk about the first order Markov chain, it is dependent only on the first previous day. So on one previous state. Let's think of it like that. And this is something that we have discussed in quite a lot of detail. But here I felt that the examples here were quite nice. So what you need to do is that if you are told that, for example, only one model exists, and in that model, for example, only one coin exists, and that coin has got a probability of 0.5 for head and 0.5 for tail, right? So what is the probability that we're going to observe 3 consecutive tails or 3 consecutive heads? So in this question, what you can note is that when I talked about only one coin, this means that there is nothing hidden there. There's nothing. The only model that exists that we're trying to work on with is the basically the single coin, right? So there is nothing hidden there. There's no transition. The coin will not change. It will always remain the same. The probabilities will always remain the same. So there is no transition between states going on. But then the second question, second thing to note is when it say that you have got tail, tail, and tail, 3 consecutive tails. This means that I'll have to compute the probability of getting the first tail. So what is the probability that the first value that I'm going to get is going to be a tail? And that is going to be followed by this on the second day. What is the probability that I'm going to get a tail given that the previous state was also a tail? And in the third day, again, I am expecting a tail. So that is the emission that's going on, given that the previous emission was also a tail. And so this brings us to the 2 main components of a Markov chain, right? So from both these examples, what you can see is that a Markov chain is going to consist of these 3 main components. First is you need to define how many states are there. So for example, in this example of weather, you have got 3 different states, right? So you can emit 3 different values. You can have 3 different values. You can either be, the day can either be hot or cold or warm. In the case of a coin, you have got 2 possible values, which is head or tails. In the case of a dice, you have got 6 possible values. And if we get any other method, you just need to identify how many states are there. So in total, there are going to be n states, each represented as q1, q2, and so on up to qn. Then this other thing we require are basically the transition probability metrics. So this is the probability of transitioning from hot to cold, hot to hot, or warm to cold, or warm to hot, or warm to warm, etc. So these are the transition probabilities that we're going to use to transfer from one state to another. From state I to state J, you need to have them such that this is another formula you need to remember. If you sum all the values that are outgoing, so all the outgoing values from hot would sum up to 1 exactly. So you can see this is 0.6, this is 0.1, and the next is 0.3, right? So if you sum it up, it's going to be 1. Similarly, if I take cold, 0.8, 0.1, and 0.1, this is again 1, and so on. So for all the outgoing probabilities, it is always going to be 1. Because from the current state, the next day, you have to observe another state in the next time frame, whatever it is, if it's a day or a minute or whatever, you have to leave this, right? And that is what you need to take care about. So that is a second important component of a Markov chain. The third important component without which we cannot have a Markov chain is the initial probability distribution over the states. So what is the probability of starting with a particular state? What is the probability that on the first state is going to be hot, or on the first state it's going to be cold, or on the first state it's going to be warm? Similarly, what is the probability that we start with the world uniformly, or we start with the word R, or we start with the word charming? In the case of a coin, it's going to be what is the probability that we're going to start with the head, and what is the probability that we start with the tail? So that is the initial probability distribution. Again, very simple. But if you sum up all these probabilities, the sum should come up to be 1, right? So let's try a few things, and that's something that you need to do as a follow-up exercise here. What is the probability that, if you use the same sample probability distribution that is given over here for weather, and for weather, let's say hot, cold, and warm, etc. And this is the sequence that we observe. 4 consecutive days that it's going to be hot, given that the initial state probability distribution, which is represented by a pi, is 0.1, 0.7, and 0.2. So 0.1 for the first state, which is a hot, For cold, we have got 0.7, and for warm, we have got 0.2, right? So with these probabilities, 0.7, 0.1, 0.7, and 0.2, which is initial state distribution. So what is the probability we start with the hot day? The answer to that is first one. So it's 0.1 multiplied by. So observing a hot day given that the previous day was hot. You again need to go here, and here you can observe that it's basically 0.6. So it's 0.1 multiplied by 0.6 multiplied by 0.6 multiplied by 0.6. And that is basically the probability of observing 4 consecutive hot days with this Markov chain, right? Secondly, if you look at it, cold, hot, cold, hot. So alternating weather patterns, and again, you can compute it by starting on a cold day, which is I think 0.7, right? Yeah, so starting on a cold day is 0.7. Then going to hot weather is 0.1. I believe, and then going from hot to cold is again 0.1, and then again 0.1, and again 0.1. So 0.1 multiplied, so we start with the cold day, which is 0.7, multiplied it with 0.1, with 0.1, and with 0.1. So these are the different things. And if you look about it, what does the difference in these probabilities tell you about a real world weather fact? The real world weather fact is that usually a hot day is followed by a hot day, a cold day is followed by a cold day, and a warm day is followed by a warm day. However, a warm day followed by a hot day is more probable than a warm day followed by a cold day. Similarly, a cold day has most chances of being followed by a cold day rather than by a hot day or by a warm day. So these are kind of the facts that you are seeing over here, and that is what it's indicating. So the idea here that I wanted to emphasize is this is simplified form of Markov chains. I gave you some examples here related to this weather example. I could have any other system. I could have a biological system here, which is showing up some values. You know, I could have a geo system here, or I could have some other system with separate states and the transition probabilities between those states. However, what you need to remember is these are observable states. These are what we can observe, and these are the direct values you're going to see in the sequence. For example, hot, cold, 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 hot, or hot, 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 right? The way you saw them. So these are all observable sequences. There's no issue like these are not observable, or there's nothing else that's problematic here. We can observe all of these. So let's look at the second part over here. And over here, again, you can see that these words are what we can observe. So if I write a sentence, are charming, charming uniformly, right? So these are what you can observe again. And since they are observable, there's nothing hidden there. There's only one model that is generating this data. In this case, this is basically a Markov chain. And remember, it will only depend on two main things. One thing is basically the initial state distribution. What is the probability of starting with a particular letter or word? And the other thing is the transition probabilities from one state to another. And of course, you also need to define the set of n states. So if we now move to the second paper over here, which is this one, it again talks the same thing, but maybe in a more complicated manner. So these are all for example, in this figure, you can see 5 different states. The type of questions that you can expect from me in the exam are that I'd ask you to identify the 5 different components of an HMM and maybe draw them like this. So you might need to draw them. So this is basically for Markov chain, but of course, when we talk about Markov models, hidden Markov models, we'll discuss what you need to display, and that it will be a similar graph. So you need to understand that very well by reading the problem statement, what constitutes what, right? And we'll see some examples here probably. So for example, over here, what has happened is that they have directly given us these 2 figures. In reality, you might be given a table, for example, with stating that current state and current state, next state, and probability of moving from current state to next state. And from that table, you should be able to construct this. Or in case of, for example, a coin, you might be given just one value, etc. So those are the things that you need to know for getting these values. For example, here you're given this state of transition probabilities, right? So I'll give you, this is the current state, this is the next state. And with this, I might ask you to, and for example, here we are given the weather on day 1. So the weather on day 1 is always going to be t is equal to 1, which is sunny, right? Given that that's the case, I might give you distributions, I might give you other values, and you'll be able to, you'll be asked to make similar graphical representation of the Markov chains or hidden Markov models. And from that, you'll be asked to compute these values, write it out like this. So this is probability of observing a data given the model. And this is something that we have done exactly in the last class. So you have those recordings there, I think. So you can go and watch that. But this is my, this is still now what we've done is we have kind of just went through the previous lecture completely. So this is kind of a feedback. And here, there are some very interesting questions that might be asked. For example, given the model is in a known state, what is the probability it stays in that state for exactly d days? So this means that after d days, it has to move out of the state, right? So given that it is in a known state for today, and it will keep on repeating the state, what is the probability that we repeat for exactly d days, and on d plus 1 day, we actually move out of the current state? And to do that, the idea is very simple. Since we are we know that we are in currently state S1. So we just need to repeat the same AII. So the diagonal, we need to just move to the same state again and again. So if I move from this state to this state, this to this state, I actually have got, if I, at the point D, I have got D minus 1 times, I'll be moving to the same state again and again and again. And since we are already in that day, so the probability of starting in that state is 1. And this comes out to be AII. So you need to go to this matrix, and these are the AIIs, and AII raised to power d minus 1. And finally, you actually have to traverse from the this state to any other state, and that is simply 1 minus AII, right? So this is the final formula that you're going to get for staying in a particular value for d number of days and exactly d number of days. And then you of course have to move out. But note the word exactly. If I remove the word exactly, then you don't need to add this one, because then you can have the same day next day, or you can actually same state next day, or you could have a different state. So it depends on the question. You need to be very careful with the question. Having said that, let's come to the other part here. And this is another example of actually how can we calculate the expected number of observations in a state. So how much time do we stay in a particular state? So in any case, I think we don't need to worry about this, and maybe move to the other problem, the problem that we need to discuss for today's class. And with the background now in place, I'll probably maybe take 5 minutes break here. You can also maybe relax a bit and then start with the next video. And the idea would be that now we're going to start with how do we extend this model, the model that we have seen for Markov chains, to hidden Markov models. And there a new concept that is of hidden states. So these states are observable states. Let's classify it like that. These are what you see in the sequence. So for example, here you want to find S3, 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 S1, S1, S3, S2, S3. And that means that S3 is basically sunny, S2 2 is cloudy, and S1 is rainy. And you can see all of them, sunny, sunny, rain, rain. And these are exactly the same states that you see that you observe in this model as well. So these are all observable. These are all there for you to see, and these are all the sequence given is exactly of this order. If you see something like this means you have to apply Markov chains and not HMMs, right? However, with the hidden state being introduced, that we'll do in the coming lecture, remaining lecture, we're going to see that these states that you're seeing over here, we'll introduce another layer on top of it, which is the hidden states. And they'll have a slightly different model to work with. So let's take a break for around 5 minutes, and let's come back and let's discuss, hidden Markov models from this point. I hope that everything till this point is clear. I've given 2 examples. In terms of quiz, if I give a question from this part, it's going to be, I'm going to give you some descriptions of the model. So you'll get some descriptions here. And from that description, like you can see over here, you'll have to come up with the model, the graphical representation of the model. And from that graphical description of the model, you might be asked to compute the probability of a particular observable sequence, or that could be one question. Or another question could be that I could ask you to give me the Q matrix, the A matrix, and the pi values from the description. So from the description, you draw this, and you also extract these 3 elements of the Markov chains. So those are the questions you need to be prepared for. Okay, let's gather again in 5 more minutes, take 5 minutes rest, and then you can continue on with the next video that is also posted along with it.